All right, welcome everyone. I hope you all had a good 2 weeks. That everything's fine with you and your families. Everybody's doing okay. I know not everybody's an Armstrong. I want to give my condolences on the loss of your sister. I'm really, really sorry to hear that. I'm glad still showing up. Okay, so I hope everybody else is doing all right. We are basically today um, going to start with calculus for real, right? So we've been doing all of this stuff with limits the last few days. We've been doing limits, and now we're going to really put these limits to use in some of the fundamental applications of calculus, which is finding tangent lines to curves and understanding how to compute velocities for particles in motion. Okay, so this is the main plan for today. But at the beginning, I want to start by going over the homework. Thank you, as always, to those of you who submitted solutions to the exercises. That was several people this week. So I was really happy. I'm always happy to get your solutions, even if there's some mistakes. That's good. And I'll always get back to you and point out the mistakes and so that you can understand the material better. So maybe before we go over the homework exercises, I want to just recall these things that we talked about last time, which are going to be important for the homework exercises and then also important for what we do today. So if you remember last time, we talked about these one-sided limits where we had to take limits that went from the left or limits that went from the right. And the results were different depending on which one we did, right? So we had the definition from last time was that if a was a real number, then we had the limit as x approaches a plus. That's the limit as x approaches a from the left. Sorry, from the right is equal to L. That means that we can make the values of f of x as close to L as we like by taking x sufficiently close to a, but also greater than a. So as a picture, the idea is here's a, and you're looking at the x values approaching a from the right. Okay? And similarly, if a is a real number, we say that the limit as x approaches a from the left, a minus of f of x is L, if we can make the values of f of x as close to L as we like by taking x sufficiently close to a and less than a, right? So the picture of this situation is we're taking a limit as x goes to a, but it's approaching a from the left. We're only looking at x's that are less than a. And then we have this fact that just the plain limit as x approaches a of f of x is equal to L if and only if both of the one-sided limits are L. So coming from the left is going to give you L, and coming from the right is going to give you L. Okay, so that's what we talked about last time in terms of one-sided limits, and we'll see in the homework some questions involving one-sided limits here. Okay. So that was the main topic from last time. By the way, just a reminder to please type your name into the chat so that we have your record for attendance so that we can give you data next week. So if you haven't done it already, please type your name into the chat. Okay. And then the other thing that we talked about last night was continuity, where we had this definition that a function is continuous at a real number a if the limit as x approaches a of the function is actually equal to the value of f at a. So it means to evaluate a limit is the same thing as just punching in the point where you're evaluating the limit. So instead of the limit as x approaches 1 of f of x, if f is continuous, you can just write f of 1 instead of the limit as x approaches 1 of f of x. Okay, so these were the two major topics from last time. And so now, with that quick review in mind, I want to go back over the homework exercises that we had from last time. So here we had homework exercise 1. So the graph of a function g of x is given. I have to redraw the graph so we can see it. So let me just look up the graph that I drew last time. so that I can redraw this. We're here. Right. Okay. So let me draw this graph. So this is what the graph looked like. So we had 1, 2, 3, 4, 1, 2, 3, 4. Function went like this. Boom. And then we had an open circle here that went up like this. And then we had a closed circle here and going down. And these points were labeled. This point was labeled as 0, 3. And this point was labeled as 2, 3. This point was labeled as 2, 1. And this point was labeled as 4, 4. Okay. So we had this function. This was the graph y equals g of x. And so this question asked several sub-questions. So we wanted to know at which, and you know, assume this goes on, right? Okay. So the question asked at which values is g of x continuous? That means the limit as you approach that x value is the same as the actual value of the function there. And then the other thing we wanted to know is does the limit as x approaches 0 of g of x exist? And then what about the limit as x approaches 2 of g of x? Okay, so let's answer. So this is really 3 questions. So let's answer the 3 questions. So where is it continuous? All right, does anybody want to answer for which x values is this function continuous? Several people submitted solutions. So, and usually for this question, your solutions were correct. If anybody wants to contribute an answer. Anybody?
Yes.
Yes, Charles.
Yeah. Sarah, I can my work is not here now, but what is the question?
So the question is, I drew this function here, and the question is, which are the x values where this function is continuous? Or maybe the same question, which are the x values where the function is not continuous? Right? I mean, it's going to be continuous everywhere except some places.
Yeah, okay. So if you look closely, you will see that it will discontinue when x equal to 2, when x is equal to 2, x is equal to 4, where we got 4, 4, you know, because there's a breakage there. And yes.
That's it. Perfect. Yeah, so that's great, right? So this function is continuous everywhere except when x equals 2, right? At x equals 2, we have what's called a jump discontinuity. That means the value of the function goes from 3 all the way down to 1 and continues. In particular, the limit as you approach 2 from the left is going to be 3, but the limit as you approach 2 from the right is going to be 1. Right? The y value, as x approaches 2 from the right, the y values are approaching 1. That's this 0.21. And as x approaches 2 from the left, the y values are approaching 3. That's this 0.23. So those limits are not the same. So that means the function is not continuous at x equals 2. And then at x equals 4, you have what's called a removable discontinuity, which means that the limits from the left and the right are both 4, right? I mean, both cases, this graph is going toward the 0.44, but the actual function is not defined at 4. That's the meaning of this empty circle that I've drawn over here at 4. It means that the function itself is not defined at 4. And so what that means over here, so this at x equals 2, this is called a jump discontinuity. And at x equals 4, this is called a removable discontinuity. Okay, that meaning it's removable because if you just defined the function at 4 to be 4, then you wouldn't have the discontinuity anymore. It's kind of very easy to fix. But it's still discontinuous, right? Because there's a hole in the graph, right? The limit, remember, to be continuous, the limit has to be equal to the function value. So in this case, the limit is 4, but the function value is not 4 because the function is not defined at 4. That's what it means to have this missing point in the graph. Okay? So that's where this is continuous. It's continuous everywhere except x equals 2 and x equals 4. Okay, so the second part asks, does the limit as x approaches 0 of f of x exist? Well, looking at the graph, does it look like it exists? Well, let's look at the function around x equals 0, right? I mean, this is a nice, smooth, continuous line, right? And it passes through the point 0, 3, right? So this means that as x gets close to 0, what's happening to g of x, or to y, which is the same thing as g of x? Well, as x gets close to 0, it looks like g of x is getting close to 3, right? And it doesn't matter which side you come from. It doesn't matter whether you come from the left or whether you come from the right. In both cases, the function is getting close to 3, right? So that means about the limit, yes, it exists, right? So the limit as x approaches 0 of g of x, we can just tell from looking at this graph. You don't have to do an algebraic computation. You can just look graphically. Remember, that's one of our ways of talking about limits. We have tables of values, we have algebra, and we have graphs. In this case, all that you're given is a graph. So anytime you want to answer a question, you've got to answer it graphically. So Benson says, yes, it exists, and that's right. It does exist. And in fact, it's equal to 3. Okay. So when you go to 0, the function goes toward 3. Okay. And so the third part says, what about the limit as x approaches 2 of g of x? Does that exist? Well, we've kind of already showed that the function's not continuous here. And the problem is that when we approach from the left, that's different from when we approach from the right. Right? So when we approach from the left, so the limit as x approaches 2 from the left of g of x, well, what are the values getting closer and closer to as the function goes to 2 from the left? The y values are getting close to this value over here, right? So that's 3. Whereas the limit as x approaches 2 from the right of g of x, which means we're coming from this side, what are the function values getting close to? Even though f of 2 is equal to 3, right? This is, if you plug in 2 to the function, you get 3. That's why this dot is filled in, whereas this dot is empty, right? So f of 2 is 3, but for values that are close to 2 but greater than 2, remember, that's what you're looking at when you're approaching from the right. Those values, sorry, I called it f, I mean g, those values look like they're going toward the y value over here, which is 1. So the limit as x approaches 2 from the right of g of x is equal to 1. And the point is this 3 and this 1 are not equal. These are not equal. And as we saw on what we reminded you, if the limit from the left is not equal to the limit from the right, then that means the limit does not exist. Okay? You have to have the left and right limits be the same for it to exist. So since left and right limits differ, we have that the limit as x approaches 2 of g of x does not exist. Okay, right? Because even if the two side this limits exist on each side, they have to agree with each other in order for the total limit to exist. So a place where the total limit exists would be a point like x equals 4, where the limit of these function, the limit of this function is 4, regardless of which side you approach from. Okay. All right. Any questions about any part of this problem? Okay. No questions? Okay, it's clear. All right. So let's move on to question number 2. So question number 2 asks for what value of c is the function f of x continuous everywhere? So here we have f of x is being defined in a piecewise fashion. It has one definition for when x is less than 2. It's going to be cx squared plus 2x. And it's going to have another definition for x greater than 2, which is x cubed minus cx, or x greater than or equal to 2. And we want to know, when will the entire function be continuous? Well, I'll just say certainly as long as x is not equal to 2, then these functions are just polynomials. We think of c as being some constant that we're going to choose. So whenever x is not equal to 2, the function f is just given by a polynomial. And one of the things we learned last time is that polynomials are always continuous. So I'll say that as just away from x equals 2, f of x is a polynomial. And so it is automatically continuous. Okay, so we only need to check x equals 2, right? And so in particular, we need remember the definition of continuity over here. Continuity, the function is continuous at 2, let's say, if the limit as x approaches 2 of f of x is equal to f of 2. So we need to evaluate f of 2 and show or figure out which values of c actually give the correct limits. Okay. Okay. So any idea how we should start this problem?
Yes.
Yes, Charles?
So if the limit of a function exists, that limit should equal to f of L. If the limit of the function is equal to L, then it must also be equal to f of L.
Right.
That means if we just evaluate the function at L,
right,
the value we're going to get should be equal to the limit. That's what it means.
Right. I think you want to evaluate it. Usually we'd say at A, not at L, right? 2 is
okay.
the A.
Okay, at A. Right. So we try to check and see if that will hold. Yes. Yes. So then we can just go ahead and say x cubed minus cx should just be equal to x is greater or equal to 2. So in place of x, you can put 2 there, and then you cube it, and then you have cx, which will be 2c.
Right.
So you get that expression. Then we can also find, the limit, as the limit of the function as x goes to a minus or a plus. A minus, and then we can do that evaluation. Then
Mm-hmm.
if we do that evaluation, going to have is that we're going to have the limit of f of x is equal to L, which is also equal to f of L, and, and then we can, is also equal to um, the limit of the function f of x as x approaches 2 from the negative side,
Right. So which
and then
expression do we
we,
use when we're approaching 2 from the negative side?
we use minus.
Right. So, but which expression for f
Minus.
for the function?
Come again?
Right. So f has two different expressions. So when we're approaching 2 minus, which of the expressions for f of x do we use here?
Or we use the one that is less than 2.
Exactly. Right. So this is going to be c times 2 squared plus 2 times 2. Right. We're plugging in as we approach this. This is what's going to happen as x approaches 2 of this equation. Right. I mean, maybe I'll add one extra step. Let me say this is equal to the limit as x approaches 2 minus of cx squared plus 2x, right? We use this expression for what happens when x is less than 2, because that's what's going on when x is approaching 2 from the minus side, right?
Yeah.
This over here is c times 2 squared plus 2 times 2, or that's equal to 4c plus 4. Okay? Great. So what about from the plus side? Well, so from the plus side, right, we need to use, if we're approaching 2 from the positive side, then which expression do we need to use for f of x? We're looking at values of x that are greater than 2. So we need to use this second one, right? X cubed minus cx. That's what happens when x is greater than 2. So when we go from the plus side of f of x, what we're really using is the limit as x approaches 2 plus of x cubed minus cx, right? Which is, we can just plug in 2 because it's a polynomial, and that gives us, as we've seen before, 2 cubed plus c times 2, which is equal to 8, sorry, minus c times 2, which is equal to 8 minus 2c. Okay, so we have that the value of the function is 8 minus 2c. The limit from the left is 4c plus 4, and the limit from the right is 8 minus 2c, right? Because we're using these two different expressions for f, depending on whether we approach from the left or whether we approach from the right. Okay? So we want to know what's going to make f of x continuous. We have two different expressions here, but we want to know when they're continuous. So how can we solve for the correct c that's going to make this function continuous at x equals 2? What equation do we need to write down?
What?
Yeah.
You just...
Sorry, question?
By equating the two values.
Mm-hmm. Yeah, it's only at the value
the
2.
left side to the right side.
Yeah.
So before c plus 4, we
Yeah.
got 8 minus 2.
Exactly. So we set these equal to each other. Right, so we set these equal to each other. So that's 4c plus 4 equals 8 minus 2c. And then we can solve that. We can add 2c to both sides. So that's 6c plus 4 equals 8. And we can subtract 4 from both sides. So that's 6c equals 4. And then we can divide both sides by 6. And that's going to give us c equals 4/6, which is the same thing as 2/3. Right?
Correct.
Yeah.
Correct.
And so this is what we need over here is 2/3. Right? So, I mean, in the end, you're just plugging in 2 to both of these expressions and setting them equal to each other. But I want to have all these words over here so that we really know what's going on in this problem. It's not just saying to do some algebra. You need to interpret the meaning of what the question is asking, right? So the question is saying, where is this continue, for which values of c For every value of c, this is a different function. It's saying what kinds of c's can we plug in that will make it continuous everywhere? And what we say is, well, no matter what we plug in for c, it's always going to be continuous away from x equals 2. So x equals 2 is the only point we have to check. And there we have to check that the limit from the left is the same as the limit from the right. And those are both the same as the actual value of the function. But in this case, the value of the function is the limit from the right, so there's no difference. So normally we'd have to set all three of these equal to each other. But in fact, for this function, two of them are clearly equal already. So you only need to solve for setting 4c plus 4 equals 8 minus 2c. Okay? And so the value of c that solves that is c equals 2/3. Okay? James, yeah?
I got a question.
A little bit. It's not so clear, but I hear you a little. No, not anymore. Not getting you anymore. Yeah, hi. I hear you. It's soft, but I do hear you.
Yeah. I got a problem. I don't understand the solution. 4c plus 4 equals 8 minus 2c. And we're going to call it like 10. That means 2c across. And 4 is a constant. So we can carry across to get to that.
Yeah, I mean, you mean could you factor out a constant here? You could, but I don't think you need to, right? So we're trying to do 4c plus 4 equals 8 minus 2c, right? So I'm just trying to get all of the c's. It's a constant, but it's also a constant we're trying to solve for. So in the context of the function, it's a constant, but then in the context of this equation, it becomes a variable that we want to solve for, because we're trying to figure out, what is the right constant. So we set up an equation in terms of the constant, but then we need to solve that equation for c. So while we're solving this, c basically becomes like a variable that we're trying to solve for. And so this is a linear equation. We just think of it for the variables. What we're doing is we're getting all of the c's on one side, and we're getting all the constants on the other side. So I'm moving the 2c over to the left-hand side. That gives me 6c plus 4 equals 8. And then I move the 4 over to the right-hand side. That gives me 6c equals 4. And so in the end, we can solve for c.
Okay, I understand.
Is that okay? Okay, good. Other questions? Okay. Okay, so let's do the next assignment. Okay, so I must confess the problem. This is not the problem I meant to assign. I meant to assign the limit as x goes to -3, not the limit as x goes to 3. So I made a mistake when typing the problem. But let's answer the problem as it is. So it says evaluate the limit as x goes to 3 plus of x plus 2 over x plus 3, and then also the limit as x goes to 3 minus of x plus 2 over x plus 3. So let's recall, this is called a rational function. Rational function. Right? And the rational functions, and so remember that to do limits of rational functions, how can you evaluate limits of rational functions? You can just punch in the limiting value as long as it doesn't make the denominator 0. So you can do this as long as it doesn't make the denominator 0. Okay. So you can punch in the limiting value as long as it doesn't make the denominator 0. So in this case, if we're plugging in this limiting value 3, limiting value meaning where we're taking the limit 3, does that make these denominators 0?
No.
No, right? because it's 3 plus 3, which is 6. So in this case,
Correct.
this just tells us that both limits are just what you get when you punch in 3. So just 3 plus 2 over 3 plus 3, or in other words, 5/6. So just punch in 3. That's all that you have to do for this problem. Now, what I meant to ask is the same problem, but with -3 instead of with 3, right? So maybe I'll ask that now. What's the limit as x approaches to -3 from the negative side of x plus 2 over x plus 3, and the limit as x approaches -3 from the positive side of x plus 2 over x plus 3, right? So here you can't just punch in 3. You can't just punch in -3 because it's going to make the denominator 0, right? So here you can't just punch in x equals -3, right? Because if you do that, then the denominator is 0, and it's going to be undefined, okay? So the question is, for this limit, what we're really saying, what's the limit as x approaches -3 from the negative side, right? Let me just draw a number line. So if here's -3, this limit's coming from this side, the other limit is coming from this side, right? Okay, and so the question is, what happens when we approach 3 from the negative side? So that means our x value is going to be something that's just a tiny bit less than -3. So as x approaches 3 from the minus side, x is a small bit less than -3. So what does that mean for the denominator? So x plus 3, if I take x to be a tiny, tiny, tiny bit less than -3, what does that tell us about x plus 3? What kind of number is that?
You will get a positive number. The difference will be positive.
Not quite, right? Because x is less than -3.
Will be a
Right.
negative value.
It'll be a negative value, right? Because x is a little bit less than -3. So when we add 3, it's going to be a little bit less than 0. Right? So x plus 3 is a small negative number. Okay? And in fact, this is getting smaller and smaller as x approaches -3. Oh, sorry. This is I meant to write -3 there. Sorry. Let me. That's x approaches -3 from the negative side. Right. So if we look at what happens with this fraction, we've got an x plus 2 on the top. X plus 2, as x is approaching -3, x plus 2 is just approaching -1, right? Because x going to -3 just means that x plus 2 goes to -1, right? I mean, you're just adding it up. So what we're looking at with the limit is we're looking at values that are just a little bit less than -3. And so what these values are approximately is -1 over a small negative number. So I'll say as x approaches -3 minus, then x plus 2 over x plus 3 is approaching -1 over a small negative number. And when I say a small negative number, it's a number that's really going to 0. So in the limit, if I've got a -1 in the numerator and then something that's very small and negative in the denominator that's going to 0, what is that fraction going to? Yep. So what is that going to approach?
It's getting.
Well, positive value.
Right, positive value. And what positive value? If the denominator is going to 0 and the numerator is going to 1 or to -1.
Come again?
So if the numerator is going to -1 and the denominator is also negative but is going to 0, then what positive value are we really approaching?
It's like it's going to positive infinity.
Infinity, exactly. Right, so this goes to positive infinity, right? Because the denominator is going to 0, the numerator is not going to 0. The numerator is -1, right? So we got -1 over something going to 0. So it's going to be some kind of infinity, but it's going to be positive infinity because both the numerator and the denominator are negative when we approach -3 from the left, right? This is negative over negative. So we're going to get positive, and it's going to be positive infinity. Okay, so the limit as x approaches -3 from the negative side of this rational function is going to be positive infinity. Okay, right, it's going to be positive infinity. Okay, so this is a little tricky. We'll do the other side also. And also, I mean, nobody worked on this because this isn't the question that I asked in the homework. But I want to go over this because this is the question that I meant to ask in the homework. So first, any questions about this? We're going to do the other side also. But before we do the other side, questions about x approaching -3 from the left. Okay, let's do the other side. I'll add an extra page here. So let's now evaluate the limit as x approaches 3 from the positive side of x plus 2, sorry, -3, limit as x approaches -3 from the positive side of x plus 2 over x plus 3. Right, in this case, we have, if we approach -3 from the positive side, we're going this way, then when we take, in this case, x plus 2 is still approaching, -3 plus 2, which is -1, same as before. But now, x plus 3, we're looking at numbers that are a little bit greater than -3. And so if it's a small bit greater than -3, then when we add 3, it's going to be a little bit greater than 0. So this is approaching 0, but it's always going to be positive numbers as it's approaching 0. So the limit, what we have for x plus 2 over x plus 3 is that it's approaching -1 over, well, x plus 3 is approaching 0. So when you get close to 3, what you have is a very small positive number. Yeah, sorry. Have a very small positive number. Right. So in this case, we have a very small positive number. So as this denominator goes to 0, which is what's happening as x goes to -3, our numerator is -1, our denominator is a small positive number. So what does the quotient go to?
The quotient will go to, hello?
Yeah, hello, Gabriel.
Yeah, the quotient will go to negative infinity.
Exactly. Right, so here the quotient goes to negative infinity because it's still going to some kind of infinity because you've got a 1 in the numerator and you're going to 0 in the denominator. But in this case, your denominator is positive and your numerator is negative. So the function's actually going to negative infinity. So I'll actually just show you what does this graph look like roughly. We have, we're looking at -3 over here. What it turns out the graph actually looks like is that we have what's called a vertical asymptote here. And what the function's actually going to look like when we go to 3 from the positive end, it goes to negative infinity. So it's going to look something like this at x equals 0. Yeah, so it's going to look like that. And then as we approach 3 from the left, it was going to positive infinity. So that's going to look like this. Okay, so this is actually what the function looks like. You can graph it on a calculator if you want to. But this is the actual graph. Okay, and in fact, there's going to be what's called a horizontal asymptote over here. Imagine that's horizontal. There's going to be a horizontal asymptote at x equals 1, but let's not worry about at y equals 1, but let's not worry about that yet. Okay, but the point is, as you go to -3 from the right-hand side, you're going to minus infinity. As you go to -3 from the left-hand side, you're going to plus infinity. Okay, and this is, you have to do this reasoning because you can't just plug in -3. Because if you try to plug in -3, you get the denominator is 0. So you don't get a number that makes sense. Okay. All right. Any questions? Okay. All right. So this last one I'm just going to do because it's hard to have you draw a graph while you're here. So draw a graph of a function f of x satisfying that the limit as x approaches 0 from the left of f of x is -1, the limit as x approaches 0 from the right of f of x is equal to 2, and that f of 0 itself is equal to 1. So let me just say, how would we draw something like this? Well, let me look at x equals 0 over here, if this is x and y. Well, I want the limit as x approaches 0 from the left of f of x to be equal to -1. So maybe I'll draw something like this, where it ends up at -1. I'm going to draw an open circle here because f of 0 is not -1. F of 0 is actually 1. So I'll put that point over there. Right. Okay, I'll put the point 1 over here. So this is -1, this is 1, and then we want the limit as x approaches 0 from the right-hand side to be equal to 2. So I'll draw maybe something like this. Okay, so this would be the kind of function that I would look for. Okay, here, the way we see it is like oops, I did not mean to do that. What did I just do? No. There we go. Okay. Right. So the point is the function, the limit from the left, the limit from the right, and the actual value of the function are all 3 different things, right? So
Correct.
so here from the left we have -1. The value of the function itself is 1, and from the right we have 2. Okay, so of course, it can really do anything away from 0. That's not what the question is asking, but a correct answer will look something like this. Okay, so I just want to do that because it's kind of hard to draw with you telling me how to draw. All right, any questions on this? Okay, people are quiet today. All right. Okay, so let's get into the new lesson then. Let's get into today's. So this we just recalled. So let's skip ahead over here. So today we're going to introduce the derivative, right? So this is, maybe the most important class we're going to have of this semester because this is, the fundamental concept of differential calculus. Okay, so we've done enough work with limits now. We're ready to talk about what a derivative means. Okay, so it's time to introduce the derivative. And so what is the derivative? I'm not going to tell you yet, but it's a concept that allows us to solve two seemingly different but very deeply related problems. So one of these is called the tangent problem, and one of these is called the velocity problem. Okay, so I'll talk about them roughly on this page, and then we'll talk about them in more detail on the next pages. So the tangent problem says, how can you figure out the slope of the tangent line to a curve? Okay, so we'll draw that. We'll draw pictures of that. And then the velocity problem asks, if an object is in motion, how can you calculate its velocity at any given time, right? I mean, it's one thing if the object is moving at a constant speed or a constant velocity. You know, if you're driving at 40 miles an hour, then that's your speed. It's 40 miles an hour. But if you're getting faster or slower, how do you know how fast you're going at exactly a given time, right? I mean, this is a question like, how does a car's speedometer work? A speedometer is supposed to tell you how fast you're going at a given time. Usually you say speed is distance over time, right? But in order to calculate distance over time, you need to really be talking about multiple times, right? So what does it mean to talk about your speed at any given time? So this is the velocity problem. This is the question. And it turns out that both of these problems can be considered under the umbrella called calculating rates of change. And, you know, this is what the derivative does. So the derivative does. Okay, and if you want a reference for this, so in the textbook that I sent you, that I sent to the group a while ago by Stuart, this is Stuart chapter 2.1, everything that we're going to talk about today. Okay. Okay, so let's draw some pictures. Okay, so first of all, what is a tangent line? What does it even mean? Okay, so let's say that I have a circle. So if I have a circle, I can define a tangent line at a point on the circle to be the line that touches the circle only at that point, right? So the tangent line here means a line, it's going to be this line right here. It's the line that touches the circle only at one point, right? This over here is the tangent line. This over here, we'll call this the tangent line. Okay.
Yeah.
But yes, Charles?
Yeah. I just want to add to what you just said.
Mm-hmm.
The line touches the circle at one point,
mm-hmm.
and the radius of the circle is perpendicular to the tangent line at that point.
Yeah, that's true. So if I draw the radius of the circle here, then it's going to form a right angle with the tangent line there. Yeah. Great. Yeah, so this it happens to be perpendicular to the radius. Now, the problem with this whole picture is that, okay, for circles, this is great. The tangent line hits the circle at one point. But for most other graphs, this definition just doesn't work. Okay, so here's an example. Let me look at a line, I don't know, something like something like this. Let's say I take this curve. And I want to understand the tangent line at this point. Well, there's lots of lines that only touch this curve at one point. I mean, I could draw this line. It only touches the curve at one point. But that's not the tangent line, right? The point is the tangent line's not supposed to slice the curve perpendicularly. It's supposed to go along the same direction of the curve. So this red line is no good. We're not going to use that. So instead, what happens if we draw the tangent line the way we're supposed to? So it kind of is going in the same direction of the curve like that. And now if I continue this line, it will touch the curve at a second point, but that's fine. We don't care. And that's the reason the definition of the tangent line is not really a line that touches the curve at one point. Okay, for a circle, that definition works. But for more general curves, that definition just doesn't work. right? This line is the tangent line, even though it touches the curve at 2 points, whereas that first line I drew is not a tangent line, even though it touches the curve at 1 point. So the better way to think about the definition of a tangent line is that it's the point that goes in the same direction of the curve at that point, okay? Or you can think about it that if you look really closely around that point, then if you zoom in, zoom in, zoom in, zoom in, this curve is going to start looking like a straight line. And the tangent line is going to be the line that, goes at the same slope of that straight line. Okay, you can think of it as kind of the line that stays on the same side of the curve after it hits it at that point. Okay, and the fact that it also touches the curve some point over here just doesn't matter. That is, points far away have nothing to do with the tangent line. The tangent line is about what's happening close to your point, which is why it maybe shouldn't be surprising that, it's going to have something to do with limits, with all of these limits that we're studying. Okay, so in this case, this red line is the tangent line. Right? And what you're looking for is exactly this picture. The line at the point where it touches the curve is traveling in the same direction as the curve. Okay. So this is what it means. And so a big question that it's going to be, so let's say we're given a curve or a graph of, some function y equals f of x. How do we compute the tangent line?
Come again.
Yeah. So if we're given a curve that's given by a graph, y equals f of x, then we want to just know this. So this is a question. This is just a general, maybe I'll say guiding question. Okay, so if we're given a curve that's given by some graph, how do we compute the tangent line? So we'll do an example, right? But this is going to be the...
We can compute.
Yep.
Hello?
Gabriel,
We can compute the tangent line by using the first principle order or derivative.
Right, okay, but we're assuming nobody knows what a derivative is yet. So what we're trying to do is kind of derive what the derivative is and what it means. Okay, so how do we compute the tangent line? So let's try to do this for an example. Okay, so let's look at the parabola y equals x squared, and we're going to look at the point 2,4 on the parabola. So I'll just draw this. We'll do this. So we have our parabola y equals x squared over here. And maybe this here is the point 2, 4. And this is going to be our tangent line to the parabola. It's going to look like this. Okay, at that point. So what we want to do is compute the tangent line to the parabola of y equals x squared at the point 2,4. Now, the key thing we need to know how to do is to compute the slope, right? Because if we can compute the slope, if we call it m, we know that this line has to contain the point 2,4, right? It's got to pass through the point. So if it has slope m and it contains the point 2,4, then we know the equation of the line. We can compute the line because we can use the point slope form of the line. So whatever the slope m is, the equation of the line has to be y minus 4 equals m times x minus 2. Right? This is the point slope form of the line. So the whole problem is to compute the slope, right? That's what we need to do. If we can compute the slope, we win. Okay. And now usually if I give you a line and I tell you to compute the slope of the line, what you need to have is 2 different points on the line. You need to say the slope, here's 2 different points on the line. The slope is the rise or the change in y value divided by the run or the change in x value. But in this setup that we have here, we're only given 1 point on the line. We only know 2,4. We don't know any other points on the line. So what are we going to do? Well, the idea is, let's look at the line passing between this point and some other point on the parabola. Okay, so we'll look at the line passing through 2,4 and some other point on the parabola. So we can compute that slope. And then what we're going to do is we're going to take the limit as this other point on the parabola gets closer and closer to 2, 4. And I'll draw a picture of this on the next page. But what we'll see is that we have all these different lines that as the 2 points get closer and closer together, these lines are starting to approximate the tangent line. Okay, so this is going to be the idea. We're going to carry it out on the next page. So I'm going to draw this picture again on the next page, but I'm going to do it bigger. Okay, so let's draw the picture. So recall we're computing the tangent line to the parabola y equals x squared at the point 2, 4. So let me draw this bigger. I'm going to do here, the algebra is going to be over here. This is going to be the algebra. This here is going to be the geometry. Okay, so let me draw the graph. So I'm going to draw the parabola. It's going to look like this. Here's my point 2, 4. And now what I'm going to do is I'm going to take a lot of different colors and I'm going to draw a lot of different lines. So I could draw the line going between 0, 0 and 2, 4, right? So that could be a straight line. It'll look something like this. Let me see if I can, I think I can do this so that they're actually straight lines. Yeah. Okay, so that's a line going from between 2, 4 and 0, 0. Let me use a different color. So this would be, you know, for instance, this here would be, you know, 0, 0. Well, I could take the point 1, 1. I'll put that in a different color. Now I'm going to take a point that's a little bit closer to 2, 4, call this 1, 1, and I could draw the line between 1, 1 and 0, 0. So something like this. Sorry, 1, 1 and 2, 4. Right? So I could draw that line. And then I could take a point that's maybe even a little bit closer. I'll draw this in orange. So maybe a point that's even a little bit closer to the blue point. And I'll draw an orange line that goes through the two of them. So right, and so on. And what we see is as the point, so as the second point gets closer to 2, 4, the lines get closer to the tangent line. Right? The tangent line I'll draw in red. So the tangent line is just going to be the line that goes through, oh wait, sorry. Tangent line is just going to be the line okay, so it's a little bit hard to see, but what you should think about this is that we have a green line, and then we have this purple line, and then we have this orange line, and what it's all trying to approach ultimately is this red line, which is the tangent line. So the tangent line is in red. Okay, these other lines are called secant lines. So the green, and the purple, and the orange lines. So these lines are called secant lines. Okay. So the point is, as my other point on the graph is getting closer and closer to 2, 4, all of these secant lines are secant lines between 2 points that are getting closer and closer together. And in the limit, what you end up getting is actually the tangent line. Okay, so this is the geometry of the situation, right? We keep drawing lines where the points are getting closer and closer together. And in the limit, what we end up with actually is the tangent line. So now what's the algebra over here? Remember, so this is the graph y equals x squared. So before I move on to the algebra, does this geometric picture make sense?
Certainly, it makes sense.
Okay, good. Right, everybody else is clear? Okay, so what's the algebra? Well, the algebra says the slope of the secant line between, let's say, 2, 4, which is one of our points. And what's the other point? Well, the other point is just some point on the graph. This is the graph y equals x squared. So if I have a point on the graph x comma y, it's always of the form x comma x squared, right? Because it has to lie on the graph, right? So if the x value is x, the y value has to be x squared. That's what the graph y equals x squared means. So the slope of this secant line is, well, we have to take the change in y values. That's going to be x squared minus 4 divided by the change in x values, which is x minus 2, right? This is what I'm going to call this delta y. That's the change in the y values. And I'm going to call this delta x, which is the change in x values. Or you could just call this the rise, and you could call this the run. Okay. Okay, so if I just said, here's a point 2,4, here's a point x comma x squared, what's the slope? Well, this is how you'd figure out the slope, because you know how to figure out the slope of a line between 2 points. So the only thing that makes this different, what makes this calculus instead of algebra, is that we're now going to take the limit as x goes to 2, right? Because as x goes to 2, that's what's saying that this point is getting close to 2, 4. So for tangent line, all that you have to do is take the limit as x goes to 2. Okay, so this is the key observation of differential calculus, right? Which is that in order to compute the slope of a tangent line, you have to look at the secant lines, write an expression for the slope of a secant line, and then take the limit as one of the points on the line gets closer and closer to the other point on the graph. So this is our expression for the slope of the secant line. We now take the limit as x goes to 2. So this is the limit as x goes to 2 of x squared minus 4 over x minus 2. And this is the type of problem we've seen already over the last month, right? We can factor x squared minus 4 as x minus 2 times x plus 2 and divide this by x minus 2, right? Remember, we can't just punch in 2 because we get 0 over 0. That's indeterminate. But if we factor this, we get x minus 2, x plus 2 over x minus 2. And then the x minus 2's cancel each other out, because when we take the limit as x approaches 2, it's not equal to 2. So we're allowed to cancel out x minus 2. And so this is equal to the limit as x approaches 2 of just x plus 2. And now this is just a polynomial. So now we can just punch in x equals 2 for this. So this is going to be 2 plus 2, which is equal to 4. Okay, so the slope of this tangent line, what we've just computed, is that the slope of this tangent line is going to be 4. Okay? And the way we computed it is that we computed the slope of the tangent line as a limit of slopes of secant lines. Lines between 2 points on the parabola, where one of those points just stayed put, it's 2, 4, and the other line got carried closer and closer and closer and closer to the 2, 4. And in the limit, you get the tangent line, and so the limit of the slopes is going to be the slope of the tangent line. Okay, so this is a really, really, really important idea in calculus. And calculus is not just about computing tangent lines to curves. This actually interprets lots of practical applications, which I'll talk about at the end of today, or maybe a little bit next time. But I don't want to move on from this slide if people are confused. So I really want questions right now, if anything is not clear, because this is really, really fundamental. And everything that we do from now on is going to be based on this picture. Okay, so any questions about how we did this process for computing the tangent line, or computing the slope of the tangent line? Okay. All right. So if it's clear, let me talk about how this works in general. So how does this work in general? So suppose we have any graph, y equals f of x, and we have a point a comma b that lies on the graph. That means
Yeah.
b is equal to
Hello,
f of x.
Dan.
Yes, question?
Hello.
Emmanuel? No. Okay. Okay. So we want to compute this tangent line at a point where AB,
You
where
get
B.
me?
Oh, sorry. Emmanuel,
Hello?
question? Yes, Emmanuel? Hello?
Yeah. Could you
Yeah.
please go back to the slides? Let me
Yeah.
please. Could you please go back to the slides?
Yeah, it should be there.
You getting me?
Yeah, I'm getting you. I went back to the slide. Can you
Hello?
see it? Yes, I'm getting you.
Okay. Yeah. Yes. My
Yeah.
network is not too ready here today,
Okay.
but actually I was thinking, uh, the question only provided 1 point.
Right.
You getting me?
Yes, I'm getting you.
Hello?
Hello, yes, I'm getting you.
Because my understanding, the question, I mean, this graph, they want you to find the tangent line. Eh?
Mm-hmm.
Okay, I'm saying they only provided 1 point. How
Right.
did you arrive at the slope when they
Right.
provided only 1 point, which
Right.
is
So
2,4?
right. So this is the entire process. So we have to do it
You
indirectly.
getting me?
Yes, I'm getting you. Are you getting me? I hear everything. Are you getting me?
Yeah, I'm getting you. Yeah, yeah.
Okay, good. So you have to, your question is great, right? And this is the question that Newton solved, right? How do you figure out the slope when you're only provided 1 point? That seems like a hard thing to do, right? And the answer is we have to come at it indirectly. So what's going to be this red line? Well, we don't know at first how to calculate the slope of this red line. So first, what I'm going to try to do is calculate the slope of a line where we have 2 points. I'm going to take the line through 2, 4, and maybe some other point on this graph, maybe something like 0, 0. And then I'm going to do the slope between 2, 4 and some other point on the graph, maybe 1, 1. And then I'm going to keep taking other points. So we have the green point and then the purple point and then the orange point that are all going to be points on the graph that are getting closer and closer to 2, 4. And in every instance, I'm going to calculate the slope of those lines. So this is the setup over here. So if I have a point 2, 4 on the graph, and I have some other point x comma y on the graph, or that's also x comma x squared, I can calculate the slope of the line between 2 comma 4 and x comma x squared, right? If I take another point on the graph, I have 2 points. And so I can do the slope, right? And so that slope here between 2 comma 4 and x comma x squared is going to be x squared minus 4 divided by x minus 2, right? This is the standard way of doing the slope if I have 2 points. So are you getting me so far? I haven't finished yet, but I'm saying this is our setup. We imagine that we're not actually doing the tangent line, but we're taking the slope between 2, 4 and another point on the graph. Okay, and if that other point is just given in terms of x, then the slope that you get is x squared minus 4 divided by x minus 2. Is that okay? I'm worried the network is losing you. Yes, getting you. Okay, good. So if that's the case, then what do you have to do to get the tangent line? Well, the tangent line goes through 1 point, but we have 2 points. So in order to get the line through 1 point, we have to take the limit as one of the points gets closer and closer to the other point. And in the limit, they're going to be the same point, and we're going to get the line through just that point. Okay? And what that means in terms of algebra over here is we have to take the limit as x goes to 2. Okay? Limit as x goes to 2 is what happens when this x squared point becomes close to the 2, 4 point. So we take the limit as x goes to 2, and that will give us actually the slope of the tangent line. And then this limit is the type of limit problem we've been doing for October. So we know how to solve this limit problem, and we end up getting that the slope is 4. Maybe I should, just for completeness, we should write down the equation of the line. If the slope is 4, then the equation of the line, I'll put it in another page. So the equation of the tangent line in point slope form is going to be y minus 4 equals 4 times x minus 2, right? That's the point slope form. Or we have that's y minus 4 equals 4x minus 8, which is the same thing as y equals 4x minus 4. Okay, so this is another way of, we could write it in either of these ways, is going to be the equation of the tangent line. But the point is, the hard part completely is figuring out the slope. Once you know the slope, then writing down the equation of the line is easy because you have 1 point. Okay, so I think Emmanuel Che's network failed, so he probably didn't hear that, but it's probably good for everybody to hear it one more time. Okay. All right, so any further questions on this? Okay. Okay. So how does this work in general? So let's say we want to compute the slope of a tangent line to a curve given by y equals f of x at a point a comma b. So here I'm just going to draw a generic curve, y equals f of x, and this here is going to be the tangent line. Maybe I'll draw it in a different color. Let's draw the tangent line here. Okay, that's going to be my tangent line to the curve at some point a comma, oh, no, wait. At some point a comma b. Okay. This is going to be my point. So what do we do? Well, the idea is look at the secant line between a comma b, which also is the same thing as a comma f of a, right? Because b is equal to f of a. That's what it means that it lies on this graph. And we take any other point on the graph. So we could take x comma f of x for any other point on the graph. So, and then the slope of the tangent line is equal to the limit of the slope of the secant lines as x approaches a. Right? So in this diagram, we could take some other point. Maybe this is some other point over here. This is x comma f of x. And I could look at the secant line that goes between these 2 points. And then I could take a closer point, which maybe I'll draw in purple, a closer point over here. And I could look at the secant line that goes between this point and a comma b. Okay, and what we see is that as we have the green line, then the purple line, eventually, as my point gets closer and closer to AB, I'm getting closer and closer to the red line. So the slope of the secant line is equal to the limit of the slope, the slope of the tangent line is the limit of the slope of the secant lines as x approaches a. So algebraically, what is this? Algebraically, the slope of the tangent line at x equals a is, well, we have to take the limit as x approaches a of the slope of the secant line. Well, this is the line between a comma f of a and x comma f of x, right? These are our 2 points. And so that slope is just rise over run. So that's f of x minus f of a divided by x minus a. Okay, so this here is the rise, and this here is the run. Okay, and this is our formula. Okay, so this is our formula for figuring out if I have a graph y equals f of x, and I want to know what's the slope of the tangent line at x equals a, the answer is I use this formula. I take the limit as x approaches a of f of x minus f of a divided by x minus a. Okay, and this is exactly what we did in the last example. Here, f of x was x squared and a was 2. So we did x squared minus 2 squared divided by x minus 2. That's how it worked in the last example. Okay. So each one of these is the slope of a secant line, and we're taking the limit as x approaches a, as the 2 points on the secant line get closer and closer together so that we end up with a tangent line. Okay, and so this is important enough that I'm going to write it on its own slide, right? So the slope of the tangent line to the graph of y equals, what do I want to say? The slope of the tangent line to the graph of y equals f of x at the point a comma b is exactly this limit. This is just rewriting what I wrote the last time. And sometimes you can make a change of variables. So if you make a change of variables here, h equals x minus a, right? If we have this change of variables, h equals x minus a, that tells us that x is equal to a plus h. So we can substitute this in. If we make a change of variables, h equals x minus a, then f of x becomes f of a plus h. F of a stays f of a. X minus a here just becomes h. And instead of x approaching a, if we want to write everything in terms of h, what this is telling us is that h is approaching 0, right? Because if x is approaching a, then their difference is approaching 0, right? X minus a is approaching 0. So this formula is equivalent to this formula. There are certain situations where this formula is a little bit easier to work with than this formula, and there's certain situations where this formula is easier to work with than this formula. But both of these formulas here are equivalent. Okay, so this is our procedure. How do we figure out the tangent line to the graph? We have to evaluate this limit. But usually it's pretty straightforward, right? Because we have our point, we have our function. So this just tells you exactly the limit that we have to evaluate. And the only problem is how do we do it, right? How do we evaluate these limits? And the good thing is this is what we've been practicing for the last month. So we have some ideas for how to evaluate these limits. And we'll do some examples for practice. Okay, but let me just go back to the picture, right? The picture is what explains what's happening. We're taking a bunch of lines that are getting closer and closer to the tangent line, and in the limit, they are the tangent line. Okay, and so in the limit of the slopes is going to be the slope of the tangent line.
Yeah.
Yeah, question? Charles?
No, comment.
Yes, comment. Yeah.
Yes. Okay. So when you look at the equation that, finding the tangent line, when we take the limit, in fact, this particular equation is called the difference quotient.
Difference quotient, yes. Yes. So rise over run. This part over here can be called a difference quotient.
So when the limit of this function exists, that limit is actually the derivative of the function.
Yes. So I haven't used the word derivative yet, but I'm gonna call it over. Where am I gonna? I'm gonna do it on slide 18. So it'll happen on slide 18. Okay. Yes, but okay. This is the derivative. So if anybody's heard the word derivative, this is all that it is. Okay. It just means this limit. Yeah, but so we'll discuss it after we do velocity and position. Okay. Okay. So let's do another example. we're going to compute the slope of the tangent line to the graph of y equals square root of x at the point 9, 3. So what does the graph of y equals square root of x look like? It looks like this. This is y equals square root of x, and this will be the point. This is 9, this is 3. This is our point 9, 3, and we can have a tangent line at this point that's going to look something like this. Yeah, let me draw that better. Ugh, no. It's hard to draw these tangent lines accurately. That's better. That's better. Okay. So that's going to be our red tangent line. So now we don't need to write down all of these points and clutter our diagrams. At this point, we can now go right to the formula. It's going to be the limit as, the limit as x approaches a of f of x minus f of a over x minus a. Right? So we have the limit as x approaches a of f of x minus f of a over x minus a, which in our case, we have that f of x is equal to square root of x, and a is equal to 9, right? Because 9 is the x value. A is always the x value here. Always, always, always the x value. So this gives us the limit as x approaches 9 of square root of x minus square root of 9 over x minus 9, or well, which is the same thing as the limit as x approaches 9 of square root of x minus 3 over x minus 9. Okay. So we've seen, so again, we can't just punch in x equals 9, because then we would get square root of 9 minus 3, which is 3 minus 3, which is 0, divided by 9 minus 9. We would get 0 over 0. So we can't just punch in x equals 9, because you get 0 over 0, which is meaningless. But we've seen examples like this. Okay, so we've seen examples like this where we have to evaluate a limit that involves a square root. So who remembers what we have to do to simplify this expression in order to evaluate the limit?
Yeah.
Yes, Gabriel?
Yeah. But there are many methods we can use. We can use factorization.
Mm-hmm.
We can use rationalization.
Yeah, let's do that.
Which method you want to use?
Yeah, let's do rationalization. So what do we want to multiply the numerator and denominator by?
The rule of x plus 3.
Exactly. So we multiply by the conjugate, right, over the root of x plus 3 times the root of x plus 3 over the root of x plus 3. This is fine. We can always multiply by 1. And remember, this here is called the conjugate.
Yeah.
Right. Great. And so when we do this, in the numerator, remember we have, this is something of the form a minus b times a plus b. So the result is a squared minus b squared, right? So it's square root of x squared minus 3 squared. And then over, I won't simplify the denominator for now. I'm just going to get x minus 9 times square root of x plus 3. But the point is, this becomes x minus 9 divided by x minus 9 square root of x plus 3. And now we're in good shape, because now we have an x minus 9 and an x minus 9. And that's going to cancel out. So what we're left with is the limit as x approaches 9 of 1 over square root of x plus 3. And now we could also, I see Robert, yes, we could also factor the denominator as square root of x plus 3 times square root of x minus 3. That's completely fine, and that works too. And then you could get a simplification. Either way is completely fine. And now we have something where we can just plug in x equals 9, right? Because this is now no longer going to make the denominator 0. So what we get here is just 1 over square root of 9 plus 3, and that's equal to 1/6, which is going to be the answer. Okay. So this is it. we have to calculate this limit. These limits will always be somewhat interesting because they're always, if you've set them up right, they're always going to be of an indeterminate form 0/0. And once you have a 0/0 limit, you need to be creative. You need to find some cancellation. But we've seen a lot of these examples over the last month. So when it's something that involves a square root, then the way you do this cancellation is by multiplying by the conjugate, or as Robert said in the chat, you could factor the denominator as radical x minus 3 times radical x plus 3 and cancel out a factor of radical x minus 3.
Or,
Either way is okay. Yep.
Or you could use the L'Hospital method as well.
The what method?
The L'Hospital method.
Okay.
Differentiating both the numerator and denominator.
Okay. Yeah. Yeah. So there's lots of methods that you can use.
Yeah?
Yes. I just said yes. So there's lots of methods that you can use.
Sure.
Yeah. Okay, but in any case, you're going to get this answer here, which is 1/6. So if you look at the slope of this line, it's going to have slope 1/6. So it's going to have 6 units of run for every 1 unit of rise over here. Okay, and so this lets us calculate the slope of the tangent line, right? You just have to evaluate this limit. All right, any questions? Okay, so in the end, it just comes down to evaluating a limit. You just need to know what's your a, that's always the x value, and what's your function, that's just the graph. In this case, it's square root of x. Okay, so let's shift gears and talk about it. We've been talking about tangent lines. So let's talk about a different problem now. This is called the velocity problem. So let's say that the position of a particle moving in a straight line is given as a function of the time t. This should just say in a straight line as a function of the time t is given by an equation s equals f of t. So the position is a function of time. So the question is, how can we compute the velocity of the particle at time t, right? This is what your speedometer is doing in a car, right? The speedometer tells you exactly how fast you're going at a given time, right? So it's telling you what's your velocity right now. Now, usually what we would compute is the average velocity between two times. And this is exactly going to be one of these, difference quotients. That Charles was talking about, where this thing over here, or difference quotient that Charles was talking about, where this over here is what's called your displacement. And this is the change in time. Right? So normally in algebra, if you're trying to figure out velocity, what you take is your displacement or your overall distance traveled divided by the amount of time, right? Distance divided by time equals speed, right? So if you have 2 points, if I know I'm here right now and I'm somewhere else in an hour, I can calculate what's my average speed over that hour, right? And this is not a calculus problem. This is just an algebra problem. If I travel 50 miles in 1 hour, then my speed is 50 miles an hour. Right? But that requires knowing where I am now and knowing where I am in an hour in order to make that calculation, right? So instead, if we want to do this instantaneously, we have to take a limit as our time interval gets smaller and smaller. So we have to take the limit as the second time approaches the first time. If I want to know what's happening right now, I don't want to know where am I going to be in an hour. I want to know where am I going to be in a split second, in a teeny tiny amount of time. That's what's going to tell me my instantaneous speed. So we have to take the limit as t2 approaches t1. So this may be clarified. We're going to do an example, but you should already see that this looks very similar to what we were doing with tangent lines, right? It's still the same kind of difference quotient, except instead of a rise over a run, it's representing a displacement divided by a change in time. Okay. So let's do this with an example. So in physics, one of the things that we know is that if you take an object dropped from a building at time t equals 0, the position, the amount that it moves, is 4.9 times t squared, where t is the time. And this is where s is the distance from the top of the building in meters and t is the time in seconds. So let me just draw a picture here. So we have here, let me draw this better. So here's our building. This is our building, and here's you, and you have some object that you're dropping, right? And so this object is falling due to the force of gravity, okay? And after how much distance has it fallen? This is S, is the distance in meters. So it's the distance fallen in meters in time t seconds. Okay. Okay, so there's a physics equation that governs this that you've probably seen, which is that S is equal to 4.9 times t squared. Okay, we're measuring the distance traveled. If you're doing it in coordinates, it would be minus 4.9 times t squared, but that doesn't really matter. If you're doing it in feet instead of meters, this becomes 16 instead of 4.9. But let's stick with meters. So the question is, what is the velocity of the object after 3 seconds? Okay. Oh, sorry. No, decline. Okay. What happened? What just happened? Sorry. Okay. No, sorry. Yeah, that's fine. Okay, great. Okay. 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 So this is the amount of time. So what is the velocity after 3 seconds? Well, let's go what we have here. So we can look at t time t equals 3. That's 3 seconds after you drop it. So t is 3 seconds after you drop it. It's probably going to have to be a pretty tall building for it to still be falling after 3 seconds, right? If you just drop it off a 1-story building, it's going to hit the ground before 3 seconds. So let's imagine the building's tall enough that it's going to keep dropping. T equals 3. And now let's pick some other point. Maybe we'll call it, T2 or something like this, which is going to be just some other time. T2 is going to be some time after 3 seconds. So we can take the average velocity between 3 and 3. So the average velocity from t equals 3 to t equals t2 is exactly this difference quotient. It's going to be s of t2 minus s of 3 divided by t2 minus 3. Right? This is exactly what we have from the previous page. This is the distance that it travels, and this is the time. Okay? Right? It's the position at t2 minus the position at 3 divided by t2 minus 3. This is kind of how much it travels between 3 and some other time t2. If we want to know the velocity at 3 seconds, so to get the velocity at t equals 3, what do? Well, we do the same thing we did before. We have to take the limit as t2 approaches 3. Okay, so we're going to take the limit as t2 approaches 3. So this is the limit as, say, t2 approaches 3 of s of t2 minus s of 3 divided by t2 minus 3. Or in other words, so the function s is given by 4.9 t squared. So this is 4.9 times t2 squared minus 4.9 times 3 squared divided by t2 minus 3. So sorry, limit as t2 approaches 3. This. Okay. Okay, so this is what we have to do to calculate the velocity. We do, again, this difference quotient, which gives you an average velocity, and then we take the limit as the second time approaches the time that we care about. Just like with the secant line, we took the limit as the point approached the point we care about. With time, we take the limit as the time approaches the time we care about. So let me just evaluate this on another page. So I'll rewrite this problem. So this is, we want to do the limit as t2 approaches 3 of 4.9 t2 squared minus 4.9 times 9 divided by t2 minus 3. Sorry, question?
Hello? Yeah, Karobor?
Yes, Enoch?
Yeah, it's
Yeah.
Hello?
Yes, hello. I'm getting you. You're soft, but I'm getting you. Hello? 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 Okay. All right, sorry, I'm not getting you right now. So let me just do this limit quickly. So I'm going to pull out a 4.9. This is 4.9 times the limit as t2 approaches 3 of t2 squared minus 9 over t2 minus 3. If you plug this in, you'll get 0 over 0. So you can ask it on the chat, Enoch, if you want to. So this over here looks like 0 over 0. So instead we factor out. This is 4.9 times the limit as t2 approaches 3 of t2 plus 3 times t2 minus 3 divided by t2 minus 3, right? I'm factoring out this t2 squared minus 9. And then again, we get a cancellation of these t2 minus 3s. And so we end up with 4.9 times the limit as t2 approaches 3 of t2 plus 3. And now we can just punch in t2 equals 3. And so this is going to be equal to 4.9 times 6. Or in other words, that's 29.4 meters per second is the velocity. Okay. Okay, if you can ask, you can type a question into the chat if you want. Okay, so this is how we do this limit. So the speed after 3 seconds is going to be 29.4 meters per second squared. Velocity has a direction, so we should say downward. 29.4 meters per second. And this is exactly how we do it, right? So it's exactly, we take the same difference quotient and we take the limit as t approaches the time that we care about. That's how we do the velocity of the object after 3 seconds. Okay. Questions? Okay. From the previous problem, what if you were given an initial position and the final position? Well, then you could figure out the average velocity. And there's various ways to soup up this problem. But right now, I'm trying to just do kind of the basic of how these limits factor into calculating instantaneous velocities. So yeah, so there are lots of different ways that you could jazz up this problem to make it a little bit more difficult. But if you're given an initial position and a final position, then you'd need to know how much time that would take. You'd still need, the equation of motion. For this problem, I'm giving the equation of motion to start. Okay, so let me just say what's going on in general here. Well, if we have the position of a particle moving in a straight line, if it's given as a function of time t by s equals f of t, then the velocity of the object at time a is given by the limit as t approaches a of f of t minus f of a. This here, remember, is the displacement between time t and time a. And this over here is the time elapsed, right, from t to a. And this entire thing here, the displacement divided by the time elapsed, is another one of these difference quotients. Okay. This is a difference quotient. If this limit exists, that's what the velocity of the object at time A is. And again, we can make this same change of variables, just like what we have before. We can change, if you want to work it in terms of h instead of in t, then this limit is also, the limit as h goes to 0 of f of a plus h minus f of a over h. Okay? And if you notice what these formulas look like, they're exactly the same as the tangent problem, right? Everything's exactly the same. It's just that all the x's became t's. Okay, that's the only difference. Okay, so this calculating the velocity at a given time is exactly the same thing as calculating the tangent line or the slope of the tangent line to a curve. In fact, it's exactly the same limit that you have to evaluate in order to do it. Okay, and they both come from taking the limits of these difference quotients, where one of the difference quotients represents rise over run. That's the tangent problem. And one of these difference quotients represents displacement over time elapsed. That's the velocity problem. Okay. So this is exactly the same as the solution to the tangent problem. Okay. So let me mention that. So what's the derivative? So Charles mentioned the derivative. So the derivative encodes the common solution of both of these problems. What if you want to find the slope of the tangent line without the use of first principle of derivative? Well, eventually we'll have formulas for the derivatives. Those we'll do next week. But for now, we only have the first principle because I'm trying to define what the derivative is. Okay? Yeah, so we'll do those next week. We're going to derive the power rules next week. Yeah. Okay. So the derivative encodes the common solution of both of the above problems. So this is a definition. So if we have some function f of x, then the derivative of f of x at x equals a, and this is an incredibly important notation, so you'll see this a lot. It's written f prime of a, f with a little dash here, f prime of a equals this limit as x approaches a of f of x minus f of a over x minus a. Or equivalently, the same thing, f prime of a is the limit as h approaches 0 of f of a plus h minus f of a over h. Okay, both of these, remember, are equivalent. You're just making a change of variables, h equals x minus a. Okay? And what does this derivative do? It gives the slope of the tangent line to y equals f of x when x equals a, and I'll say it also gives the velocity at time a if f of x is the position function. Of time. Okay? So, right, so this derivative, this limit does the tangent line if you want, and it also does the velocity if you want. Okay, and so this is what we mean when we say take the derivative. Now, as Enoch is getting at in the comments, and as some of you know, there are various shortcuts that you can use for calculating the derivative. So there's something called the power rule. There's something called the chain rule. There's something called the product rule. We're going to talk about all of these rules next week. But for now, I'm not assuming that anybody necessarily knows how to do derivatives, right? It's supposed to teach. So can the function and its inserted values be shown graphically? Yes. Yes. Enoch, you may have missed this. We started all the way back here with graphs and geometry over here. So they'll be in the slide. So we've already seen this function in the geometry for the algebra. Okay. But let me say, yeah. So we could do this. Yes. So maybe, yeah. Okay. So Enoch wants to do this. Yeah. Let me add, sure. I'll add one extra page where we talk about this function. So here we had s equals 4.9 t squared. So we could do a table of values, right? So this is time t, and this is, s equals 4.9 times t squared. So at time 0, this is 0. At time 1, this is going to be 4.9. At time 2, this is going to be 19.6. At time 3, this is going to be 4.9 times 9 is going to be 44.1. I think, no. Yes, 44.1. And then at time, 4, it's going to be 4.9 times 16, which I can't do on my own. So 4.9 times 16, this is going to be 78.4. So for instance, we could say the average velocity from t equals 2 to t equals 4 is 78.4 minus 19.6. That's the change in distance, divided by 4 minus 2, which is the change in time. And that's equal to, this is equal to 29.4. And look at this average velocity from t equals 2 to t equals 4 actually is the same as the answer that we got. They're both 29.4. But that's a coincidence, okay? That has something to do with how this particular function works. This isn't something that's always going to work, right? So going from 2 to 4, in this case, we did the average velocity between 2 and 4. That gives you the instantaneous velocity at 3, but that's not always the case, okay? But it's a good approximation. Okay, so let me just wrap up because we're running out of time. So the last things that I want to say is that if y equals f of x, right, the slope of the line connecting 2 points on the graph, we can think of it as the average rate of change of y with respect to x between those 2 points. Similarly, the derivative, f prime of a, is the instantaneous rate of change of y with respect to x at the point given by x equals a. Right, so these derivatives are representing a rate of change. That's what a slope of a graph is. The slope is the rate of change. So if f of t is a function that represents position at a time t, then f prime of a represents velocity at a, as we've seen. And so now it seems like this derivative actually can represent lots more things, okay? Anything that has to do with the rate of change, this derivative represents. You're welcome. So for instance, if f of t represents the concentration of a reagent in a chemical reaction at time t, then f prime of a represents the rate of the reaction at time a. If f of x represents the population of a colony of bacteria at time t, then f prime of a represents the rate of population growth at the time a. Basically, anything that involves continuous rates of change can be modeled by the derivative, right? If f is equal to, so if f is equal to a quantity, then f prime is equal to the rate of change of that quantity. Okay. So this derivative is not just about finding slopes of tangent lines. If that's all that it was, then calculus wouldn't be so important. The point is that this derivative can describe change for any kind of thing that changes. And so that can be biology, bacteria colonies, that can be chemistry, rate of a reaction, that can be physics, looking at velocity, that can be economics. You can talk about the rate of change of how much it costs to produce something, depending on how much you want to produce. So in all, fields of quantitative science, this derivative shows up. Okay, and we'll talk a little bit more about that next time. All right, so homework exercises. First one is calculate the tangent line for the graph of y equals 1 over x at x equals 1. That's going to be just like these tangent line questions. Second one is a physics question. So the position of a particle moving in a straight line is described by s equals t squared minus 8t plus 18, where s is measured in meters and t is measured in seconds. What is the average velocity of the particle between t equals 3 and t equals 4? What is the instantaneous velocity at t equals 3? And what's the instantaneous velocity at t equals 4? So these are going to be like the last question that we did in terms of physics. And then 3 is a little bit more of a thought question. So there's no numerical answer for 3. So it says the number of bacteria after t hours in a controlled laboratory experiment is n equals f of t for some function f. So what is the meaning of the derivative f prime of 5? What does that mean? And if there's an unlimited amount of space and nutrients, which do you think is bigger, f prime of 5 or f prime of 10? And if the supply of nutrients is limited, does this change your answer? Okay, so this here is a little bit open-ended. So we'll discuss it next time. You're not going to be able to use any formulas to answer this question. But there is some content here. Okay? So thank you again for your attention. And next week on November 22nd, we're going to obtain various rules for computing derivatives. So various shortcuts that you can use to compute derivatives. Okay? So thank you again for your attention. As a reminder, always, please, please, please type your name in the chat if you have not done so already, because we want to have your record that you were here so that we can give you data next week. Okay, so anybody who has not yet typed in their name, please do so. Okay, and so we will have class next week at the usual time at 4 o'clock. Okay, all right, any last questions?
Andrew?
Yes, Abraham?
Yeah, thank you very much for the class today. I think we'll get to you because we want to give the certificate to last year's teachers.
Right,
So
they
want to,
arrived, right? Sanjay has them?
Yeah.
Okay, great.
I'll meet Sanjay for us to discuss when we actually get to you
Okay.
to give the certificate.
Did they get signed by the minister in the US, or do they still need to be signed?
Yes, he's just coming from Senegal.
The minister is here.
Oh, okay. So they still need to be signed?
Okay.
Yeah.
Okay.
I'll try to follow up on it.
Okay, but that's good. They're in Liberia, so that's great. Okay. Taking a while.
Hello.
Yes. Hello? Okay, good. Hi, Prince. How are you?
Yes, sir.
Yes.
Prince.
Prince. Hi, Prince.
Thank you. Yeah, thank you so much today. Even though I really found it difficult today with network. Trying over, yeah, that's why I was not very active in the class as normal. But lastly, I saw the performance and this, and it was okay. But still, I will try to download it and then go through to try for next class. Thank you so much. Thank you for this effort you are showing to us.
All right, you're welcome.